virtual classroom of Chem-based School of Chemistry. Sound clear? Today I'll be starting on the chemical equilibrium. In fact, this is the we'll be starting on chemical equilibrium, which is reactions which is reversible, meaning reactions where reactants give products and products give reactants. Say, for example, if I react A with B, that gives C and D, and then in reverse, the C and D, the products react to form the reactants again, A and B. These are referred to as reversible reactions. Reversible reactions are reactions where reactants give products, and then the products react back to form the reactants again. This happens under certain conditions. We'll be discussing them later on. And there are some conditions like, for example, the whole system has to be in a closed vessel, the closed system, for it to be reversible or to reach equilibrium. I'll explain the difference between reversible and equilibrium shortly. So, to represent the reversible reactions, we use this type of half-headed reversible arrows. Right? It is not arrows like this. This is wrong. Not fully headed reversible arrows like this. This is used for a different purpose. We'll be studying in A levels. And for reversible reactions, what we use is this type of half-headed reversible arrow. So reversible reactions are reactions where reactants give products and products give reactants under the same conditions of temperature, pressure and concentration. So those three conditions are important to mention. You will know shortly the reason why temperature, pressure and concentration should be kept constant in a reversible reaction. Now, some reversible reactions occur spontaneously, meaning naturally it is reversible, but some reversible reactions you have to control the conditions in order for it to be reversible. For example, the reaction of nitrogen gas with hydrogen gas to form ammonia is a reversible reaction, right? That means if you keep the whole thing in a closed vessel, the ammonia will decompose back to form nitrogen and hydrogen. And also hydrogen gas reacting with iodine gas to form hydrogen iodide. This is also a reversible process. Sulfur dioxide gas reacting with oxygen gas to form sulfur trioxide. It's not that all have to be gases. Reversible reactions occur in different physical states as well. Now these reversible reactions which I listed here, there is no change in the reactants or the products. I mean, there's no color change occurring as the reactants form products or as products form reactants. There is no color change occurring, but certain reversible reactions, there is a color change which is taking place. For example, if I take the reaction between dinitrogen tetroxide and nitrogen dioxide. As for dinitrogen tetroxide, it is colorless. Nitrogen dioxide, it's brown. So you can see a color change here, two colors, and then ammonia gas reacting with hydrogen chloride gas to form ammonium chloride solid. This is a reaction between gas and solid. Reactants are gases, products are solid. This is colorless and ammonium chloride is white. Right? So these reversible reactions, you can see a color change occurring, and the above three reversible reactions which I mentioned, there is no color change whatsoever. Now, when a reaction, a color change occurs, that doesn't mean the colorless disappears and brown appears, and then the brown disappears and colorless appear. You will see in the reaction vessel both colorless and brown, both white and colorless, but colorless turns brown, brown turns colorless. So that's what is meant by reversible. But some reversible reactions, reversibility can be controlled. Like, for example, when you change conditions, it becomes reversible. Otherwise not. For example, you know the hydrous copper sulfate pentahydrate, which is a blue color solid. This is blue in color, which is known as a hydrous copper sulfate. When you heat this, it loses the water of crystallization and forms the anhydrous copper sulfate. It loses the water of crystallization and forms the anhydrous copper sulfate without water, which is white in color. But when you cool, the backward reaction will occur. When you cool, when the temperature is decreased, the anhydrous copper sulfate gains its 5 water molecules and forms the hydrous copper sulfate. So this particular reversible process, you have to change the condition in order to make it reversible. So if you heat, the forward reaction occurs. If you cool, the backward reaction occurs. Is that clear? Is it clear? Any questions? Explain what is meant by reversible reaction. Reactions where reactants give products and products give reactants under the same conditions of temperature, pressure and concentration. How a reversible reaction is shown in a chemical equation, right? By using reversible arrows. By using reversible arrows, you draw the reversible arrow. Give some examples for reversible reactions. You can copy these first 3 examples. You can copy the first 3 examples for reversible reactions. First 3 examples. What are the reversible reactions in which we can observe a color change, hence prove its reversibility? For this, you can copy these 2 examples. Colorless to brown and colorless to white. Explain experiment to show the reversible reactions of hydration of heated anhydrous copper 2 sulfate. When blue anhydrous copper 2 sulfate, which is copper 2 sulfate pentahydrate crystals, are heated, they lose their water of crystallization, resulting white anhydrous copper sulfate. If water is added to this mixture or cooled, the blue color immediately returns. You can copy the last example, hydrous to anhydrous. Both anhydrous and hydrous are in solid state. Let's see what is an equilibrium reaction and what's the difference between reversible and equilibrium reactions. Now, equilibrium reactions are reactions where when reactants react together. Now we just discussed the kinetics last week, rates of reactions. So we know initially in any reaction the rate is very high because there is a greater concentration of the reactants. Because the reactant concentration is much greater, what happens is that the reactants react rapidly and then form the products at a very high rate, because initially there is a greater concentration of the reactants. So what happens is that when reactants react initially, the rate of the forward reaction will be maximum. So you have the maximum forward reaction rate because the concentration of reactants are maximum initially. So that gives the products at a very high rate. That's what happens initially. But initial stages, the products are very less. The concentration of products are very less because just now it is formed. So then what happens is that the rate of the backward reaction is initially 0 because there is no sufficient amount of products produced to form the reactants again. But gradually, as more and more products are produced, the backward reaction will slowly start. That happens gradually, right? So rate of the forward reaction is maximum initially. As more and more reactants get used up, the forward reaction rate will slowly drop, because with time, more A and more B reacts to form more C and D. As a result, the product concentration decreases with time, but initially it will have the maximum concentration, and then the concentration start dropping with time as more and more products are formed. Clear? So when the concentration of the reactants start dropping, the rate of the forward reaction also drops, because we just studied last week under the kinetics chapter that the concentration, if it increases, the forward reaction rate increases. The concentration drops, the forward reaction rate drops. So the forward reaction rate maximum initially, backward reaction rate is 0. As more and more products are produced, the backward reaction rate will start and the forward reaction rate will slow down. So A and B will react at a higher concentration to form the C and D at a higher rate. With time, the rate of the forward reaction will decrease. As more and more products are produced, then starts the backward reaction. But with time, the backward reaction rate will start increasing. Right? So forward reaction rate is maximum initially, it drops. The backward reaction rate is minimum initially, it starts rising. And there will come a point where both the rate of the forward and the backward reaction becomes equal. That is the point where we say the system has reached chemical equilibrium. Chemical equilibrium is a state of balance where the rate of the forward reaction equals the rate of the backward reaction. When these two rates are equal, then we say the system has reached equilibrium. So once the system reaches equilibrium, there won't be any change in the concentrations of the reactants and the products, because the rate at which the reactants form the products and the rate at which the products form the reactants are the same. These two rates are the same. Right? So because these two rates are the same, you will not see any change of the reactants or the products. The concentrations will be almost same. I mean constant. It is not a condition that concentrations have to be same in equilibrium. It may be same, but concentrations are constant, because the rate at which the reactants give products, the products give reactants, they are the same. So therefore the amount of A and B will be fixed throughout, so as that the concentration is maintained. I mean the rates are maintained, equilibrium is maintained, and the concentration of products also remain constant throughout if it is in equilibrium. So the equilibrium is a state of balance in which the rate of the forward reaction equals that of the backward reaction. If there is a slight change in the rates, then its system will not be in equilibrium. So once the system reaches equilibrium, there won't be any change in the concentration of reactants, neither the products. Right? So that doesn't mean that all reversible reactions reach equilibrium. No, it's not a condition. Some reversible reactions, the rate of the forward reaction will be more than the backward reaction. That means it will give more and more products than the reactants. So not all reversible reactions are equilibrium, but all equilibrium reactions are reversible. All reversible reactions are not equilibrium, but all equilibrium reactions are reversible reactions. Is it clear? If you need to maintain the system at equilibrium, you have to maintain the temperature, pressure and concentration throughout. If you do a change, once the system reaches equilibrium, if you do a change in temperature, pressure or concentration after the system reaches equilibrium, then the system will come out of equilibrium. That will be no more at equilibrium. So system will come out of equilibrium if these three properties are changed. Once a system reaches equilibrium, there are conditions, right? For a system to reach equilibrium, there shall be a particular temperature, a pressure and concentration. So if you maintain these three conditions, the system which is in equilibrium will be in equilibrium forever. The moment you keep changing the temperature, pressure or concentration, the equilibrium will come out of equilibrium. When I say coming out of equilibrium, what I mean is that the rate of the forward reaction will no more be equal to the backward reaction. That might give more reactants or more products. The concentrations will fluctuate. It will not be constant throughout. Right, so this temperature, pressure and concentration is very important to keep them as constant, and they are referred to as the macroscopic properties. They are referred to as the macroscopic properties. Is it clear? Reaction should be taking place in a closed system, but if it is open system, right, then the open system will allow matter to enter or to escape, right? If matter enters, say a gas has entered, it might react with the either reactants or products, or if the gases escape, then if there's one, for example, if the D is a gas, say D escapes the reaction vessel, then there won't be anyone for the C to react and form the reactant back. So therefore the system comes out of equilibrium if it's an open system. So that's why, or sometimes if C might, oxygen might enter and it might react with the C, right? So to form some other product, so it will not react with the D then, the product which is formed. So it's very important that it has to be a closed system, and that's a condition for the equilibrium. So once the system reaches equilibrium, there won't be any apparent change taking place, because consider the reactants and the products, the concentrations remain constant, but there will not be any apparent change. Apparently there is no change taking place. That means A and B concentrations are same, C and D. So if it's a reaction where equilibrium, where color change is observed, you will not see any, like you will see constant colors, like for example brown and colorless will be same intensity. You will not see the brown disappearing and colorless appearing. There's nothing like that. You will see always a brown color, same intensity as color, and the colorless will be the same intensity. Clear? Color will be the same, like the intensity of the color of reactants and the products will not change. So therefore, when you consider the overall system, there will not be any apparent change taking place. So in an equilibrium reaction, once the system reaches chemical equilibrium, overall there is no change. Dynamic meaning change is taking place constantly. There are other equilibriums also, like for example static equilibrium is also equilibrium, but they're not chemical equilibrium. That means it's a state of balance where the reactants remain as reactants, products remain as products. It won't make a change. Like in equilibrium, continually reactants are forming products and products forming reactants. So all chemical equilibria are dynamic equilibria, because reactants giving products and products giving reactants. But static equilibrium are not chemical. Static equilibrium meaning that there will be only reactants and the products, but there is no interchange taking place between them. So that is not a chemical equilibrium. So dynamic equilibrium, reaction occurring in both directions, where the rate of the forward reaction and the backward reactions are equal at constant temperature, pressure and concentration. They are referred to as macroscopic properties. In dynamic equilibrium, the macroscopic properties are constant throughout. The rates of the forward and the backward reactions are equal, and the concentrations of reactants and the products are constant, and equilibrium is achieved only in closed system, because open system may allow matter to enter or to escape. And also I explained how the equilibrium is achieved using kinetic theory or collision theory. A macroscopic property such as temperature, pressure or concentration change, the system will adjust to minimize or nullify that change, and as a result the equilibrium will shift to either reactants or products. This is very important. This is, in short, we say Chatelles principle, but they will not ask what is Chatelles principle. Chatelles is the person who put forward this principle, that what he said was which system which is already in equilibrium, system which is already in equilibrium, if you do any change in the macroscopic properties, which means temperature, pressure or concentration, any of these properties, if you change temperature, pressure or concentration, the system will adjust itself to minimize or to nullify that external change. That means if you do a change for a system which is already in equilibrium, system will not like it. System will not like it. It will try to either form more products or more reactants and minimize their external change. That's referred to as the Le Chatelier principle, right? Is it clear? So let us see how temperature affects this equilibrium. So I'm going to first explain the whole purpose of this whole study is to study how the temperature, pressure and concentration affects the equilibrium. So I'm going to first explain to you how the temperature affects the equilibrium. That means a system which is already in equilibrium, if you increase the temperature or decrease temperature, what happens? Whether it favors a forward reaction or backward reaction. Of course, we know if you do a change for the temperature, pressure or concentration for a system which is already in equilibrium, that will not be any more in equilibrium. It will come out of equilibrium. So I'm going to explain to you how it comes out of equilibrium. Whether it favors more reactants or more products, forward reaction or backward reaction. So I'm going to start with the endothermic, the temperature effects for endothermic reaction. Now when I say this reaction is endothermic, we just discussed a few weeks ago about energetics, on what is exothermic and endothermic reactions. If I say this is endothermic reaction, what is understood by this is the forward reaction is endothermic. If the forward reaction is endothermic, the backward reaction will be exothermic. Right? If the forward reaction is endothermic, the backward reaction will be exothermic. When I say forward reaction is endothermic, what is understood by that is that when more C and D produced, heat is absorbed. As the A and B reacts to form C and D, the heat is absorbed. When the heat is absorbed from the surroundings, we know that the products will be low in temperature, which is much cooler than the reactants. Reactants will be hot, the products will be cool. That means if the forward reaction is favored for endothermic reaction, this is a very important point because, every year you get questions on this, right? How to explain how the temperature affects the equilibrium. So if the forward reaction C and D are produced, temperature is dropped because endothermic. As a result, the system becomes cooler. So therefore, the backward reaction will be exothermic. It becomes more hotter, warmer, as backward A and B is formed. So what happens is that if I increase the temperature to this equilibrium, when the temperature is increased, the system will not like, of course we know the system will come out of equilibrium, and first of all it will not like the changes. So how the system will adjust is that when I increase the temperature, system will adjust to decrease the temperature. If I increase the temperature, system will adjust to decrease the temperature. Now, how it can decrease temperature? By favoring the forward or backward? I'd like to hear from you the answer. Just type the answer. If I increase the temperature for this system, the system should decrease temperature, right? That is Le Chatelier's principle. So how can this system decrease temperature? By favoring more products or more reactants? Yeah? Right. So if I increase temperature, system should tend to decrease temperature. That means it should favor the less temperature side. You will see the products are cooler, less temperature. It cannot favor the reactants because when you increase the temperature, if it favor reactants is a big problem because some more temperature will increase. System doesn't like changes. System which is already in equilibrium will not like changes. So system which is already in equilibrium, if I increase the temperature, it will adjust itself to decrease the temperature. So only way it can decrease temperature is by favoring the products because products are cooler. So for this system, if I increase temperature, it favors the products. That means system will come out of equilibrium and it favors products. Is that clear, Safia? Not the reactants, it's products. And likewise, if I decrease temperature, system will not like. It will tend to increase the temperature. So then it favors what, Sophia? A decreased temperature for endothermic reaction. It favors the forward or the backward? Yeah. If I decrease temperature, system will not like it. It will tend to increase the temperature. That means it has to favor the forward or backward? That's right, backward, because its products are, the reactants are hotter. Because backward reaction is exothermic, forward is endothermic. So this is how you explain the temperature effect. The first point is, you have to know whether it's exothermic or endothermic. That's very important. So when you explain the temperature effect, see whether it's exothermic or endothermic. If it's endothermic, then identify. As the products are formed, the system becomes cooler. As the products are cooler, as the reactants are formed, backward, it's hotter. This should be identified first. So if you increase the temperature, system will adjust itself to decrease temperature by favoring more products. If you decrease the temperature, system will adjust to increase temperature by favoring more reactants. This is how the temperature effects for endothermic reaction. Now tell me, I will leave the next part for you. The next is for exothermic reaction. I'd like to hear from you the answer. The principle is same. In exothermic reaction, the forward reaction releases heat. That means if more C and D is produced, heat is released. That means products are more warmer. As more products are formed, it's warmer. And if more reactants are formed, it's cooler, because if forward reaction is exothermic, meaning releasing heat energy, the backward reaction will be endothermic. It absorbs the heat. So for this system, if I increase temperature, it favors more reactants or products. The system will come out of equilibrium for sure, because temperature, pressure and concentration, they are macroscopic properties. So if I increase temperature, it favors reactants or products for this exothermic reaction. Yeah? Increased temperature, it favors the backward reaction. You can say it favors the reactants, or you can say it favors the backward reaction. So if I decrease temperature, what happens? The opposite. System will tend to increase temperature by favoring more and more products. That means products are much hotter. So if you decrease the temperature, if you cool the system, it favors more products. Is that clear? So the most important thing is you have to observe and see whether this is exothermic or endothermic. If this data is not given, you cannot comment. Unless, of course, if it is a combustion reaction, right, then we know it's exothermic. Certain reactions we know it's exothermic, right? So this is what I mentioned here. Effect of temperature. As a forward reaction is endothermic, it absorbs heat from the surroundings. If the temperature is increased, system will adjust itself to decrease temperature by favoring the forward reaction. More products, as forward reaction decreases the heat. Likewise, when the temperature is decreased, system will adjust itself to increase temperature by favoring the backward reaction, as a backward reaction increases the heat. Exothermic. In the given space here, I'll copy the first reaction. Right? First reaction, endothermic, and all what I have written here. Copy this. Temperature for an equilibrium, which is exothermic. As a forward reaction exothermic, it releases heat to the surroundings. When the temperature is increased, the system will adjust itself to decrease temperature by favoring the backward reaction, as forward reaction increases the heat. Likewise, when the temperature is decreased, the system will adjust to increase the temperature by favoring the forward reaction, as a forward reaction increases heat. Exothermic. In the given space here, you can copy the second example. Answer. So exothermic reaction, forward reaction releases heat, So if you decrease the temperature, it will favor what? Reactants or products? The answers, please. So you can just put a, yeah. We just discussed exothermic reaction. Forward reaction releases heat. So products are hotter, reactants are cooler. So if you increase temperature, it forms the cooler side. If you decrease temperature, it will form the hotter side. Yes, Sajid, I am waiting for the correction. So exothermic reaction, I just mentioned before. What we should do is, first of all, identify whether the forward reaction is giving heat or absorbing heat. So exothermic reaction, forward reaction, giving out heat. So reactants are hotter than the products. Products are cooler. So listen carefully. So for exothermic reaction, first we are going to decrease the temperature. Decrease temperature. So when temperature is decreased, it favors what? The products. Because products are hotter. If you decrease temperature, it favors the products. So tick should be at the products. This is the correct answer. For your answer is wrong. You understood why it's wrong? Exothermic reaction. Forward reaction is hotter because heat is released. So if you decrease temperature, system will adjust to increase temperature by favoring more reactants. More products, sorry. Is it clear? So the opposite is for when the temperature increases. When temperature increases, system will adjust itself to decrease temperature. It is favoring the backward reaction. This is correct. The next one, endothermic, is correct. If you increase temperature, it favors the products because products are cooler and they absorb heat. Endo. Okay. Try the next question, question 9. What we should write is high temperature, right, will favor what? If will favor reactants, write reactants, or will favor products, write will favor products. Okay, start. Yeah. Products. Right, so high temperature, products, low temperature, reactants. So next one, exothermic. This is hotter and it's cooler. High temperature will favor what? Just write reactants. If it's reactants, write reactants. If products, write products. High temperature will favor. How can it be products, Rajit? This is hotter. The products are hotter. So if you increase the products, will you favor the product side? It's more hotter. So you favor the reactant side, right? Is it clear? Because reactants are cooler, and you increase temperature to favor the cooler side. And that's products. Same for next one because that's also exothermic. Pressure affects the equilibrium. I said temperature, pressure and concentration, all these three factors affects the equilibrium. As for the effect of the pressure, it's very simple. First of all, pressure is affected by only gaseous systems. So we will just take this example: nitrogen reacting with hydrogen to form ammonia. So what we should do first is count the gaseous molecules. There are there are 4 gaseous molecules of the reactants. You only count the gaseous molecules. 3 plus 1, 4. There's 4 gaseous molecules here, and there's 2 here. Right? You just count the gaseous molecules, and the side where there's more gaseous molecules, the pressure is high. Side there's less gaseous molecules, the pressure is low. The side there's more gaseous molecules, the pressure is high. The side there is less gaseous molecules, pressure is low. So what you should do is, first of all, to explain the pressure effect, you see which side has more gaseous molecules. So count the number of gaseous molecules right first, and see which side has more gaseous molecules. The side which has more gaseous molecules, you put P high. The side which has low gaseous molecules, put P low. And then what happens, you can explain the pressure effect, just like the temperature effect. If you increase the pressure, system will adjust to decrease pressure. So decrease pressure meaning it will be the product side. So product side pressure is less. So if you increase the pressure, system will adjust to decrease pressure by favoring the forward reaction. Likewise, if you decrease the pressure, system will tend to increase the pressure by favoring the reactant side. So that's how the pressure affects. So first thing you should do is count the number of gaseous molecules right here, right, and then identify which side has a higher pressure and put P high, P low. Increased pressure will favor P low side, decreased pressure will favor P high side. Another example. Gaseous molecules are there at the reactants. Molecules. How to find the number of gaseous molecules? Just count the number front. Right, front. So all the answers wrong. Gaseous molecules, I said. I didn't ask the number of molecules. I said gaseous molecules. Only gaseous molecules affects the pressure. Just count the gases. This is solid, right? Carbon you can't count. Only gases. So one molecule here and two molecules there. So pressure is low here, pressure is high there. So if you increase the pressure, it will favor the backward, low pressure side. If you decrease the pressure, it favors the products, high pressure side. Clear? Sajid, is it clear? Another example. At the reactants. Reactants, how many gaseous molecules? I'm surprised how this 3 came here. You have to count the number which is front. There is no 2 here. Oxygen is 1 here, 1 molecule. Just count the number front, not this 2. You don't count 2 plus 1, 3, because this is just oxygen 1 molecule here. Yes, Safia, how many gaseous molecules are the reactants here? Sajid, I need your answer again. The correct answer. Sajid. Molecules. Products, how many gaseous molecules? 1. So the number of gaseous molecules are same here. When the number of gaseous molecules are same, the pressure is same. When the pressure is same, there is no pressure effect. That means if you increase the pressure or decrease the pressure, nothing happens. If you increase or decrease pressure, no pressure effect. For such a question, we should write the answer as no pressure effect. Because pressure can't do anything for this equilibrium. Number of gaseous molecules are the same. Clear? So remember, the pressure is affected by only gaseous systems. You count only number of gaseous molecules. You write the number on top of the reactants, on top of the products, and write higher number side P high, lower number side P low. Increased pressure will favor P low side. Decreased pressure will favor P high side. The effect of pressure applies only to gaseous equilibrium reactants. Increasing the pressure by equilibrium shifting to the side where there is a higher number of gaseous molecules. What you should do is try this question now, like I did before. Count the number of gaseous molecules, write on top, write P high, P low, and write Roman number 1, or just write A. Increased pressure will favor products. Products is less pressure. B. Decreased pressure will favor reactant. If there's no pressure effect, like in this case, 1, 1, write no pressure effect. Right? Okay, start. Products 2. So pressure is high, the pressure is low. So increased pressure will favor the reactants. Decreased pressure will favor the products. That's the second one's answer. Please check your answers. The fourth one, 9 and 10. Pressure high, pressure low. Increased pressure will favor low pressure side, which is reactants. Decreased pressure will favor high pressure side, which is products. Fifth one, 2 and 2. Pressure is equal, so no pressure effect. And the last one, solid means 0. There's no low pressure, 0 molecules. Here 2 molecules, pressure high. Solid is no, nothing, right? 0. So when you increase the pressure, it favors the products, low pressure side. If you decrease the pressure, it favors the reactants, which is high pressure side. Clear? Did you check your answers? In fact, catalyst will increase the rate of the forward and the backward reaction, so therefore equilibrium condition will be reached faster. In fact, catalyst has no effect on equilibrium, right? Because catalyst will increase the rate of the forward reaction as well as the backward reaction, so equilibrium condition will be reached faster when you use a catalyst. So catalyst will not favor the forward or the backward, right? Like, I mean, it will not give products or reactants, because catalyst will increase the rate of both the reactions by providing alternative route with lowered activation. So when you put a catalyst, the equilibrium condition will be reached faster, meaning without catalyst, if it takes 10 minutes to reach equilibrium, when you put a catalyst, equilibrium will reach in a few minutes. So the forward or the backward reaction will be fast in the presence of catalyst. So catalyst will not alter the equilibrium state. As for the effect of concentration, that's not in the syllabus, so we just need to know that concentration affects and how it affects is not relevant. And it's actually very, very simple, which is if you increase the concentration of reactants, it favors more products. I just mentioned it because when you do past papers in the old syllabus, you will come across this. It's very simple. If you increase the reactant concentration, more reactants will collide and form more products. If you increase the product concentration, backward reaction will give you more reactants. So that is the effect of the question is, Haber process is manufacturing of ammonia by nitrogen and hydrogen. The reaction is exothermic, such as why high yield of ammonia is in equilibrium favored by low temperature, high pressure, and justify the above temperature. Now, the temperature for this is 450. Why this is considered as low temperature is that when the temperature is lowered, the reaction is exothermic, that means forward reaction is hotter. So the temperature is lowered, it favors more products. As for the pressure effect, there are 4 molecules here. Pressure is high, 2 molecules there, pressure is low. So if you increase the pressure, it favors the less pressure side, meaning more ammonia. So if low temperature favors more ammonia, why don't we use very low temperature like 50 degrees Celsius? Why 450 is used? Because low temperature favors high yield of ammonia. If you use very low temperatures, it's true that you get more ammonia, but the rate of the reaction will be very slow. We know that when the temperature decreases, the rate decreases. The rate of the reaction will be very slow. So if you increase the temperature to increase the rate, the yield will be low, because low temperature will favor products, high temperature will favor the reactants, backward reaction, because it's exothermic reaction. So very low temperatures you can't use, very high temperatures you can't use, because very low temperature will favor the more products but at a very low rate, very high temperature if you use, it will favor the backward reaction. So to compromise both rate and the yield, a moderate temperature is used in the Haber process. Not very low, not very high. Is it clear? Because very low temperature favors high yield of products, but very slow. Rate will be slow. If you use high temperature, it favors the backward. So to balance the rate and the yield, because in equilibria we discuss only about the yield, not the rate. Right? To balance the rate and the yield, a moderate temperature should be used. Clear? Any questions? If you have any questions, we can tend to that.